Hello everyone. In this video we will talk about several tests for convergence, namely the integral test, comparison test, and ratio test. So we will do most of the integral test and its motivation in class, but we do want to state it because it's going to help us with our main basis for comparison. So first we have to make an assumption. So the function we will take the integral of must be continuous, positive, and decreasing for this integral test to hold. So it only works for specific kinds of functions. And then we are going to let ak, or the kth term of our series, be just plug in k to our function, right? The integer points on our function. So then the claim is that the sum of these ak's converges if and only if the integral from 1 to infinity converges. So what this means is either they both converge, either the series and the improper integral both converge, or they both diverge. Okay, so why is this useful? Well, we have the p-test for improper integrals, and now we get all of that for free, well, not free, but from the integral test for series. So what we can say now is that the sum of 1 over k to the p converges if and only if p is greater than 1. So remember here that it only makes sense to talk about 1 to infinity because, well, the integral from 0 to 1 would be like a sum from 0 to 1, but that's just two terms, and that's just always going to converge if we have finite numbers that we're adding. So this is the only one where it shows up, so we're only concerned about the 1 to infinity, and we know this converges if p is greater than 1. So the statement of the comparison test is basically the same as for improper integrals. So if we have non-negative terms, right, this is when this applies, then if the bigger one converges, the smaller one has to converge, and if the smaller one diverges, the bigger one must diverge, right? So this is basically the same. And what do we usually use for the comparison test? Well, we usually want to compare to either a p-series, right, 1 over k to the p, or a geometric series, because we already know the results for these series all the time. So let's look at an example here. So 1 over 3 plus 5 to the k. This isn't quite anything we've dealt with so far. It's definitely not a p-series. It looks close to a geometric series, so maybe we think we can compare to that. So we know that adding more in the denominator means that it's going to be smaller, and so this is definitely smaller than 1 over 5 to the k, but that is exactly 1/5 to the k, right? So this is a geometric series, and we know if r is 1/5, then this guy will converge, right? The series 1/5 to the k converges. And so given that, and this is less than that, we know that this one also must converge by the comparison test. Okay, now I want you to look at one. All right, so for your first exercise, I want you to determine if the series 1 over k plus k squared, this k goes from 1 to infinity, converges or diverges. And remember, now that we're in the land of comparison and straying away from just geometric or telescoping, this is usually the best we can do. If it converges, it's probably not going to be something that we can actually determine the actual value for. So in our last example, we saw that the series 1 over 3 plus 5 to the k converges. So then my question is, what about this one, where we just replace 3 with -3? So it seems like this should still converge, right? It still should be like 1/5 to the k. It shouldn't make a difference that I have a -3 instead of a 3. It's just not that different. But the issue, right, is I can't use comparison test anymore because when k equals 0, I have -1/2 as my first term before I get into positive terms. Plus, I have something smaller in the denominator, and thus this is greater than something that converges, so it's not a very good basis for comparison anyway. So what we'll see next is the ratio test, which will actually help us deal with something like this as long as we're a little bit clever. So here are the hypotheses for the ratio test. So the first one seems to counter what I just said would be useful, but we'll see that it's not a big deal in a second. So we want all positive terms for our series to use the ratio test. And then we look at the limit of consecutive terms. So basically, you want to think of this as comparing to a geometric series, right, where r is exactly what you multiply, or is the ratio between two consecutive terms. So here, we're saying roughly down the road, you're multiplying by L each time to get from one term to the next. So then we have a few cases. So first, if L is less than 1, then our series converges. So again, basically you want to think of this as like geometric series where r is less than 1. Our terms are getting smaller and smaller, and basically they're going to go to 0 fast enough that our sum will converge. Similarly, if L is greater than 1, just like when r is greater than 1, our series will diverge. Our terms are getting bigger and bigger as we go on down the line. And then the last case is if L equals 1, and this is a little bit different than the geometric series where it would diverge. Here, it's just inconclusive. And so next we will take a look at a couple of examples where one will diverge and one will converge with L equals 1. So let's consider just the series K. So this clearly should diverge, right? Because we're just adding more and more and more. This is definitely going to go to infinity. All these terms are positive, so the ratio test works. And so if we look at our k plus 1th term, well, that's just going to be k plus 1 over our kth term, k, and take the limit. Well, this limit is 1, right? So this is one of the inconclusive, but here we know it diverges because we can just inspect it and see this is going to diverge. On the other hand, what if we consider this p-series, right? So this guy definitely converges by the integral test. But what happens if we take our consecutive terms? So here we have like 1 over k plus 1 squared over 1 over k squared. And we don't like fractions over fractions, so we multiply by the reciprocal, and we just get k squared over k plus 1 squared, or I'll even write that out as k squared plus 2k plus 1. So again, what's the limit here? Well, we look at the highest powers, right? We see that they're both 2. We look at our coefficients. This guy's going to be 1, but this time it converges. So clearly 1, we just have to do more work. All right, so now let's look at this guy with the ratio test. Now your first instinct should be, well, negative 1/2, that's our first term. That's not greater than 0. That seems like a problem. And that's fair. But notice that every term after that, once we get a single power of 5 involved, is going to be positive. So let's just split that off. It's not going to change anything, right? We subtract a half from something finite, it's still going to be finite. So let's just look at from k equals 1 to infinity where we do have positive terms throughout. So now let's look at the ratio. So I'm just going to do the reciprocal as it is. So my first term will be negative 3 plus 5 to the k plus 1 down here, multiplied by the reciprocal. That basically just means I erase this top guy. I'm now multiplying by 1 in the denominator, and I'm multiplying by negative 3 plus 5 to the k up top. This is my ak plus 1 over ak. Now, you could do this in a few ways. You could use L'Hopital's rule here. You could also just kind of look at these terms, say that the minus 3 is not going to really matter in the long run. Either way, what you're going to end up with is 1/5 for this limit. 1/5 is definitely less than 1, and so this part converges by the ratio test, so that's finite, and then we just subtract 1/2, so the whole thing does. And now we're happy. All right, let's look at another example. All right, let's channel DJ Khaled, and we will do another example. So with this one, this is where the ratio test is really nice, because right now we have no way to deal with things like this. Geometric series have exponentials. Sure, that's great. But factorials, not something we really know how to deal with right now. So how do we do it? Well, these actually work really, really nicely with the ratio test. Let's see why. So our k plus 1 term is 2 to the k plus 1 over k plus 1 factorial. And then I'm again going to multiply by the reciprocal. So the kth term that I was dividing by, I flip it over, and that's going to be k factorial over 2 to the k. But this is super nice, right? Because 2 to the k, we just basically cancel out all but one power up here. We're left with a 2. And then what is k plus 1 factorial? Well, that is just k plus 1 times k factorial. And so my k factorials cancel, and I'm just left with k plus 1. So now we're just talking about the limit as k approaches infinity of 2 over k plus 1. And that is definitely 0, which is less than 1. And so this guy converges. And so we just kind of learned something here. Basically, factorial grows way faster than exponential. And if you want to think about why, you're multiplying a whole bunch of 2's together up top forever. On the bottom, you end up multiplying 2, and then 3, which is bigger than 2, and then 4, which is bigger than 2, and then 5, which is bigger than 2. And so you're growing way, way faster down here. So that's the basic idea there. All right, for your second exercise, I want you to determine whether the series 3 to the k over k squared converges or diverges using the ratio test. Thank you for watching.